Hello everyone, my name is Eugen Suhanek, and today I will present you my paper on supported two-phase reading, STR.
In computer-assisted language learning, reading systems commonly provide inflow support, such as glosses, translations, or annotations. This allows learners to read beyond their unaided proficiency and maintain comprehension during reading. In that sense, support works. However, it creates a fundamental ambiguity. When learners read fluently, we do not know what we are observing: autonomous processing or reliance on external support. We observe fluent reading, but not its source. And this distinction matters. In most call systems, support remains continuously available. Unsupported processing is not directly observable during the task. Instead, it is inferred from outcomes after the fact. It is not structured as a distinct, observable condition within the reading event itself. This gap has a direct consequence. If unsupported reading is not observed as a distinct condition, then the transition into it is not controlled. In current call designs, support is either always available or reduced without a fixed boundary, gradually, implicitly, or across different texts. There is no discrete transition within a single reading episode under constant input. Learners operate under mixed conditions of partial and fluctuating support. At any moment, we cannot say, is the learner reading independently or with assistance? If we cannot distinguish this, support withdrawal cannot be isolated as a variable and therefore cannot be rigorously tested. This is the methodological limitation. This limitation is not incidental, it is structural. In continuous glossing, support is always available. In adaptive or gradual fading, support is reduced progressively over time or items. In repeated reading, conditions are separated across time, not within the same episode. Across all three approaches, support is manipulated, but its removal is not isolated. There is no discrete, system-defined transition within a single reading episode under constant textual input. As a result, observed effects cannot be cleanly attributed to withdrawal. They are confounded with exposure effects, timing differences, and variation in textual input. This makes causal attribution unclear, and within episode comparison, structurally impossible. This difference becomes explicit in the table. Most existing approaches fail on the same point. They do not define a discrete transition under constant input. Continuous glossing, no withdrawal. Adaptive fading, distributed withdrawal. Repeated reading, separated conditions. Each manipulates support, but none isolates its removal as a single event. Only STR combines three critical properties: a fixed transition, identical text across phases, and irreversible removal of support. What matters here is not any single property, but their combination. Experimental control emerges from how these constraints interact, not by improving support, but by restructuring the task itself. This is what makes support withdrawal structurally isolable as a variable. Consider a minimal case. A learner reads a passage with support, then immediately rereads the same passage without it. The text is identical. No words are changed. No content is added or removed. The only difference is support availability. The input remains constant. This creates a single, discrete transition within one continuous reading episode. STR defines support withdrawal as a bounded, within-episode event under constant input. Not distributed, not gradual, but localized in time. This transition is enforced by structure, not by instruction or learner choice. STR is defined by four constraints: passage-level scope, text invariance, deterministic transition, and irreversibility. Each constraint removes a specific source of confounding. No item-level variation. No text variation. No learner-controlled timing. No return to support. These are not pedagogical preferences. They are experimental constraints. Together, they define a two-state system with a single manipulated variable: support availability. Everything else is held constant. A minimal web-based prototype was tested with 10 adult learners. Each participant completed 5 STR cycles, 50 sequences in total. All sequences were completed. There was no task abandonment. This is important because enforced withdrawal of support could reasonably be expected to reduce engagement. That risk did not materialize under these conditions. The transition was consistently enforced and functioned as a detectable boundary within the task. This demonstrates 3 things. The architecture is implementable, enforceable, and observable at the task level. It does not demonstrate learning outcomes. It establishes protocol feasibility. The key contribution is analytical. STR converts support withdrawal from a diffuse, distributed process into a time-stamped event within a controlled environment. This means we know exactly when withdrawal occurs, not approximately, not across sessions, but at a precise point within the task. This enables phase-aligned comparison within the same text. However, there is a critical issue: rereading. Phase 2 always involves prior exposure. To separate withdrawal effects from rereading effects, an exposure-matched control condition is required. STR does not solve this automatically, but it makes such a comparison possible. It defines the minimal conditions under which controlled testing can occur. This is what enables hypothesis-driven experimental design. STR embeds support withdrawal directly into the structure of the task, rather than leaving it to timing or interpretation. This structure generalizes across contexts. In print or ebooks, learners see an annotated passage, followed by the same passage without support. In digital systems, support removal is enforced at a fixed system boundary. In classroom use, teachers vary texts and difficulty, but the withdrawal mechanism remains constant. The mechanism stays fixed. Only the content changes. This separation allows flexibility in instruction without changing the underlying structure. STR does not claim learning outcomes. It specifies the conditions under which they can be tested. 2 testable hypotheses follow. H1. Phase 2 should differ from exposure-matched supported rereading in reading latency and interaction patterns. H2. The Phase 1 to Phase 2 transition should produce a measurable discontinuity in phase-aligned behavioral data. Beyond this, a key testable extension concerns transfer. Does Phase 2 performance predict performance on a subsequent unsupported transfer passage under matched exposure conditions? This is not assumed, but made empirically testable by the STR design. What STR introduces is a new unit of analysis: support withdrawal, as a controlled, observable, within-episode event under constant input. The core limitation in CALL is methodological. Support withdrawal is assumed, but not directly observed or isolated. STR defines a minimal architecture with a single, controlled transition under constant input. Unsupported conditions become observable within the task itself, not inferred afterward. Feasibility is established. The system functions reliably without task abandonment. STR enables within-episode comparison that existing designs do not structurally allow. We no longer rely solely on inference about unsupported processing. We observe a controlled transition into unsupported conditions within the reading event. Support withdrawal becomes a discrete, observable, and controllable experimental variable.